my slide?
Yes.
Thank you so much. So let me welcome you to my lecture today. It's a lecture of time series modeling, which is some moving average models. So, like I said, I've walked you through different kind of models in time series. This is gonna be another one. And today, the moving average models are for the Q. When I say Q, I'm actually referring to the order. Okay, the order could be it could then it could be one leg apart, two leg apart, three leg apart, and so on like that. Now the question is, how does a moving average models, how does it look like? Okay, when you take a look at what I have right here, this is different from what I showed you last week. This is different from autoregressive model. You're going to see that in autoregressive model, the current value of a time series is actually related to the past values. But when you take a look at what I have right here, okay, you're actually going to see that the current value of the series is actually depending on the current shock, what I call the current white noise, the value of the white noise, immediate past, and so on like that. So which means the predictors variables have past white noises. The predictor variables are past white noises. And I'm actually going to give you an example from real life situation where, moving average models applies. Now, this is a corresponding fitted model. I said, what we're trying to talk about right now, if I want to have the prediction about the value of the time series, it's actually depend on on the past white noises. Okay, if you take a look at what I have right here, you have the yt minus 1. This is the past immediate past white noise. This is past white noise, and so on like that. So what we're trying to say in essence is that the predictor variables are actually the they are the past white noises. Okay, and that's exactly what we're trying to say. So, and that was why I said the fitted MA models use the past residuals to predict future values of the time series. Now, intuition for a time series of consumer price index, which is CPI, if economic condition cause a larger than expected increase in the CPI, okay, then we might expect the CPI of next month to also be above what is expected. Okay, so I told you the other time that in my bachelor project, I actually work on consumer effect of consumer price index, the inflation rate, and the exchange rate on the gross domestic product. So in a situation where the economic condition cause a larger than expected increase in the consumer price index, okay, then it means what one we expect in the next month to come, you know, we also be above what is expected. And let me tell you something. It is only a white noise that can actually cause, a surprise. I told you the other time, when a model is entirely white noise, then it means it will be difficult. It may be difficult for us to be able to have a projection towards the future. because what is actually going to happen next, we can't really tell whether it's going to be high or it's going to be low or it's going to be positive or it's going to be negative. But you know what? What is the difference between this model and a white noise model? This is a little bit different from a white noise model, because in a white noise model, there is no predictor. Okay? In a white noise model, if you remember what I told you the other time, in a white noise model, you're actually going to have a YT equal to WT, where WT is a white noise. So, and we actually apply that model in in a situation that is stochastic in nature. Okay. Uh, Give me 1 second. Yeah, can you guys hear me now? Can you hear me?
Yes.
Okay. Thanks so much for that. Now, I'm actually going to give you another example of a moving average model. Like I said, I was trying to explain the difference between a white noise model and, and a moving average model. And I said in a white noise model, the model would be entirely a white noise. It's going to be entirely a white noise. Okay? It's going to be entirely a white noise. But the moving average model, we have the combination of the previous past white noise. Okay? And I'm actually going to cite another example right now. Another example that I'm actually going to cite is this. If I want to consider the if I consider the the volume of sales of a grocery store, you know, what they make in sales over time, a particular grocery store. Okay? And let me tell you this, at times some grocery stores, some industry, the United States, they normally give coupon. Okay, they give coupon, and you know what? These coupons, most of the time, they are unobserved. Okay, they are unobserved. They are unobserved in the sense that the coupon. What I mean by coupon is just that, okay, they give you something like a coupon where you're actually going to have um, a drastic a reduction in the amount you're actually going to pay for for a particular for purchasing a particular item. And the theory of consumer behavior, consumer would like to buy more things at a lower price. Of course, some of you have heard about the law of demand and supply. Okay, when you look at the law of demand, the higher the price, the lower the quantity demanded, and the higher the price, the lower the so the higher the price, the lower the quantity demanded, and the lower the price, the higher the quantity demanded. It means when the price is is very very high, the consumer will buy just few items. But when the price go down, consumers will buy more of the items. And in a situation where coupon have been given, at times some companies will roll out vintage of coupons over time, and this coupon it could expire, and when it expire, okay, they're going to they're going to release another coupon again. And you know what? A time series modeler, okay, a time series modeler may have a difficulty in tracking that. And in that kind of situation, what if this guy, if YT is actually the sales, okay? Then what I'm trying to say is that the unobserved, the coupon that I talk about that was not observed, okay? So what I have here is basically the it's talking about the the number of unobserved, of those coupons, in the immediate past, and this is for previous past. In a situation where you have issue like that, then you're actually going to use a moving average model, because we're not able to catch, you are not able to, it is, you did not observe that, okay? And that really affects the sales. And the way it affects the sales, okay, it affects it in a way that the prediction, okay, uh, you know, may become something complex to undertake, okay? And that is the reason why uh, in a situation like that, that we expect, uh, you know, um, the past white noises, to do the job in predicting the time series, that particular time series. Okay, now looking at moving average in another context, if you look at that, the term moving average, like I said, it was commonly used to denote forecast based on an average of past values of a time series. And I'm actually going to give an example right now. What I'm showing you right now is what we call a three moving average. What do we mean by three moving average? The three moving average means we are considering a particular day, okay? And you are considering a day before that day, a day before that particular day, and a day after that day. Okay, so in a three moving average, it means you are focusing on one day, okay, on a particular day, and you are looking at what happened in the immediate day, that is the previous day, and what happened next. Then you average that. In the case of coronavirus, we're in the middle of pandemic right now. If you check some, the website of the Johns Hopkins University that is monitoring the cases of the number of cases in the world, you're actually going to see that they normally talk about the moving average. Though at times they use the 5 moving average, 7 moving average, and so on like that. In a situation where you are talking about 5 moving average, okay, in a situation where you're talking about 5 moving average, it means you are focusing on what happened, maybe the number of cases of the virus in a particular day, then what happened 2 days before, and what happened 2 days after, and that make it to be what? That make it to be 5 days moving average. Okay, so that make it 5 days moving average. Okay, so but right now what I'm showcasing is just a situation where you are, but when you now take a look at what I have right here now for the moving average, you're actually going to see that it is not the same as the moving average models. Let me tell you something. There is moving average and there is moving average model. Okay, I'm going to say that again. There is moving average model and there is moving average. Okay, so the moving average that I talk about right here, okay, the moving average that I talk about right here is basically, it's more or less, it's looking like an autoregressive model of that 3. Can you see that now? This is looking like what we have done before. Okay, So this is looking like an autoregressive model of order 3. You can see the lag of 3. So that is why I said that. So this is not the moving average model, but this is the moving, it means what we do in the autoregressive model of order 3, I mean in the autoregressive model is more or less like a moving averages. Okay, so if you take a look at what I have right here, but you know what, let me explain that to you. Actually, what I'm talking about is just that the in the autoregressive model of order 3, okay, we normally have parameters, okay, but this is a special case of that. Why did I call this a special case? Because all the parameters here are the same, and the parameter is 1/3. If you take a look at that, the parameter, okay, the contribution of the immediate pass, okay, the contribution of the immediate pass, the contribution of past pass, and the previously existing pass. If you take a look at that, then you're actually going to see that they are not. So you're going to see that they have the same contribution. And you know what? How do I find average in statistics? So this is more or less finding an average, because when you add this to this, because we got 3 of them, we are dividing by 3. And that is the reason why I said this is a special form of autoregressive model of order 3. So it's a special form of autoregressive model of order 3 because all the parameters are the same. Because when you are calculating the average, then you normally give equal probability, to the variable under investigation. Okay, they got the same weight. Okay, they got the same weight. So what I'm trying to tell you right now is that this is a special form of autoregressive model. So just to be able to tell you, there's a difference between the moving average model and the moving average. So this is the moving average. It is not a moving average model. Okay. Now, talking about the moving average model, we want to start from order 1, just like what we did in the autoregressive model. But before I go forward, are you guys hearing me?
Yes.
Thank you so much. Okay. When you take a look at what I have right here, this is moving average of order 1. This is the way we're actually going to write the moving average of order 1. Okay. Now, what this model is actually talking about is that, okay, if I want to determine, for instance, the price, okay, of a stock right now, we talk about the Google stock the other time. What we are trying to talk about is that the price of a stock actually depends on the current shock. Okay, this is a current surprise on the system, and this is the immediate surprise. Okay, because the white noise are surprise. Okay, did you get it now? Did you get it now? So that is exactly what I'm talking about. Okay, so this is the current shock, and this is the immediate past shock. Okay, so this is being explained by them. You remember I talked about the coupons. Okay, so this and the coupons are unobserved. Okay, they are unobserved because at times the industry will roll out coupon numbers that will get expired, and they're going to roll up a new one again. We have the vintage of coupons. Okay, at different intensity of time, and that will be difficult for any industry, or you know or any grocery store or whatever, to be able to, or any analyst to be able to monitor, okay, to be able to observe, and that seriously have effect. So the A1 right here is just the contribution of the immediate past. Okay, is the contribution of the immediate past. Did you get that now? Now, I think you are getting that now. Okay, so the WT right here is a white noise. Okay, so the white noise, it follows a normal distribution with mean zero, and this is the variance. Okay, let's look at the properties of that right now. Now, looking at the properties, you remember the other time under the autoregressive model of order one, I also show you properties. Okay, we find the mean, we got a way to find the mean, we got a way to find the variance, and not only that, we are able to obtain the autocorrelation. Okay, we're also going to do the same thing right here. Now, the expected value of yt is actually going to be mu. The variance of yt equal to this, and the autocorrelation at like 1 is equal to that. Okay, and you know what, for k greater than 1, since we're talking about like 1, we expect the autocorrelation to be equal to 0. I think you know that. So these are the properties of MA1. Okay, so what that implies, of course, it implies that, you know, if you take a look at this guy here, can you see it? Can you see this sigma square W? Can you guys see that?
Yes.
The sigma square W is the variance of white noise. Okay, so which means, and you know that the variance of yt equal to the variance of white noise multiplied by this entity. And that implies that the variance of yt will be greater than the variance of what? The variance of white noise. And that's what I have right here. And why is it that this is actually going to be greater than this guy here? Is because of the fact that this is greater than 1. Because when a1 equal to 0, if a1 equal to 0, okay, you're actually going to have the variance of yt to be equal to the variance of the white noise. Okay, but you know what? The a1 is not going to be equal to 0. So that was why we said the variance of yt will be greater than the variance of the white noise. Okay, now this is what I just talked about. Since the ACF plot shows the estimated autocorrelation at different lag, so the ACF plot for a time series generated from a MA1 cutoff after lag 1. Now, let me first confirm if you are listening, if you are hearing me right now, because I want to say something that is very, very important. Are you guys hearing me?
Yes.
Thank you so much. Thank you so much. Now, do you know when we're dealing with the autoregressive model, of order 1, I could remember that I said for a model to be autoregressive model of order 1, okay, the ACF that I call autocorrelation function should decay exponentially to 0. And I also remember that I said a partial autocorrelation function, which is PACF, should cut off after lag 1. Okay, but you know what? In the MA1, you're actually going to switch that. You're going to switch that now. Now, in the MA1, it is the ACF of MA1 that cut off after lag 1. You remember what cut off after lag 1 in autoregressive model? What cut off after lag 1 is a partial autocorrelation function plot. It is a PACF plot. But in the case of moving average model of order 1, what cut off after lag 1 is the ACF plot. So you're actually going to switch that. So that is why I said you need to pay attention to this so that uh because so that you don't confuse one with the other one. Okay, so this is the MA model with MA of order one. Now, how do we derive the mean? How do we derive the variance? The other time I gave you this properly. We said that okay, the mean is actually this, the variance is that, the autocorrelation function at like 1 equal to that, and anything beyond like 1, the autocorrelation function is actually equal to 0. If you take a look at the variance here and the autocorrelation here, expression here, this is different from what we did in the AR1, in the autoregressive model of order 1. Okay, we want to have a derivation of the mean and variance right now. Now, let us assume that you are given this. Of course, giving you this model, automatically, this is MA of order 1. This is moving average of order 1. How do I know that this is a moving average? Because I have a current shock and the immediate shock. Because a moving average model, the predictors in the moving average model, they will be, they're actually going to be the past white noises. Okay. And at times you're going to have the combination of the current and the past white noises. Okay. So this is an MA of order 1. And you know what? Where the WT, which is the white noise, follow a normal distribution with me 0. For this model, you are given that it is a 0.25. How do we derive the mean of YT? Now, when I say the mean of YT, in the grocery store sales that I talk about, if YT is a grocery store sales, okay, if this YT is, the sales, recorded by any grocery store at a particular point in time, it could be Walmart, it could be Target, okay, it could be any grocery store. Now, if this particular grocery store give coupons, okay, if they give coupons, and you know what, there is no way, these are unobservable. There's no way you can observe that, okay? There's no way you can track that coupon, okay? Because they give different kind, at times you have different kind of coupons in circulation, okay? They're going to get expire and they're going to renew that again. They're going to introduce a new one. Okay, the time series modeler, we have a trouble time, catching, observing that. Okay, now if this is the model, okay, how do we derive the average sales by that particular grocery store? And that's exactly what we want to do right now. Okay, if you take a look at this guy here, that is what I put right here. So I want to find the expectation of both sides. Expectation of a constant is actually going to be a constant. And you know what? The WT and WT minus 1 are random variable. Okay. The expectation will actually attract them. And you know what? The expectation of a white noise, take a look at that. This is the expectation of a white noise. The mean of a white noise equal to 0. And you know what? The expectation of a white noise at any period, okay? Expectation of a white noise at the current period, expectation of a white noise at the immediate past period, and so on like that. The expectation will actually going to be 0. Okay, because they are unpredictable. Okay, the expected value of the residual is actually going to be 0. That's theoretically, okay, and that is why when I plug in 0 here and I plug in 0 here, automatically I'm actually going to get 2. So which means the expected value of of YT is actually 2. Okay, is there anyone who doesn't understand how I got these 2? Is there anyone? Can you guys hear me?
Yes.
Okay. Okay. So now this is how we derive the mean. Okay. So when I'm trying to talk about on average, this is going to be the average sales. Okay. in a situation where predictors are the combination of the current and the pass, you know, the combination of the current and the pass, white noises. Now, how do we talk about the variance? If I want to talk about the variance right now, of course, the variance of a constant equal to 0, so that's actually going to go away. So this is synonymous. This is same thing as writing the variance of this, okay? And if I have a situation like this, okay, then the next thing that I'm actually going to have is it's actually going to be variance of this and the variance of that, okay? The variance of this plus the variance of that. And you know what? The covariances is 0 because WT and WT minus 1 are independent, okay? And that is the reason why the covariance will be equal to 0. And that is the reason why I can actually write this in this form. Now, the next thing I'm actually going to do right now, I told you, if you got a value inside a parenthesis, so if that value want to come out, that constant value is actually going to be a squared. And that's why you have it right here. Can you see that now? Now, if this is what I have right now, I can actually simplify that. And what is the variance of WT? The variance of WT has been given here to be 0.25. So I'm actually going to plug in that. And another thing I want you to know, the variance of a white noise, whether it is in the current period or is in the past period, is actually going to be the same as the one specified here. And that is the reason why there's no difference between the variance of WT and the variance of WT minus 1. Okay? Because what are we trying to say? We are assuming that the variance of a white noise, at any point in time, it's actually going to be the same. So plugging in is 0.25 on this. If you square this one is 0.64, plugging in that, we're actually going to have is 0.25 multiplied by 1 plus 0.64. So if you take a look at this one now, why do I have this? I can factorize, okay? 0.25 is common, okay? I can bring that out, and that's exactly what I have. Then I can simplify that as well, okay? And of course, the reason why I did not want to finish this, the reason why I did not want to simplify this, because I want you to see, a trend. Now, if you take a look at what I have right here now, you're going to see that 0.25 here is a variance of the white noise, okay? And this guy here, 1 plus is 0.64, is more or less like the square of this is 0.8. Therefore, if you take a look at this, the formula is this. You remember the other time that I showed you? I'm going to take you back now. Look at that. Can you see that here? So it means when I'm giving any moving average model, if I want to figure out the variance, it's going to be so easy to do. What I just need, particularly when I'm giving moving average of order 1, okay, what I just need to do is, do I know the variance of a white noise? And do I know what is the parameter in my model in terms of A1? I'm actually going to square that and add to 1 and multiply by that. And that's exactly what we have right here. That's exactly what we have right here. Can you see that now? Is there anyone who does he understand the way I figured this out? Is there anyone? Okay, I'm going to read my chart right now. Somebody said the variance is the same because of weak stationarity. Yeah, that was the assumption. So you are right. That was the assumption that we cited. Okay, you are very correct, because we expect that the variance to be the same, because but in a situation where the variance is not the same, there's something needs to be done. But right now we got an assumption that the variance of the white noise have to be constant over time. Okay, now if you have that one now, thank you for sharing that. Now I've been able to show you how to figure out the mean, how to figure out the variance. Now the next thing that we want to do is how to obtain the correlation. And why do I need to determine the correlation? Because I need to determine the correlation because I will need that for the autocorrelation plots. Okay. Now, if I want to find the correlation at like 1, of course, this is the formula with the covariance of, you know, of 2 time series variable that is 1 lag apart divided by the square root of the variance of yt multiplied by the square root of the variance of yt minus 1. Okay, so you get it now. And where yt equal to this, take a look at that. These are yt. And you know what? I may want to substitute for yt minus 1. If you take a look at this, if I come to this and I say t minus 1, if I say minus 1, I'm going to have this one. And I have to come to this and say minus 1, I'm going to have this one. And I have to come this place and say t minus 1 minus 1, and that will be t minus 2. So which means if this is yt, that this guy here is going to be yt minus 1. Why do I need a yt minus 1? Because if you look at the correlation, okay, there's yt minus 1 here, there is yt minus 1 here. Okay, so and if you look at the numerator right now, okay, the numerator is this guy here, the covariance. Okay, now if I want to rewrite this guy now, what am I going to do? I'm actually going to write, what is my yt? Look at my yt. Can you see my yt? What is my yt minus 1? That is my yt minus 1. Then I'm actually going to write everything right here. Can you see that now? Then I need to put a comma, okay? Now, when I do that, the next thing that I'm actually going to do, if you look at the mu here, it's a constant. This is another constant. I can basically write just only this and this. And that is the reason why you have that here. Can you see that now? Okay, if this is what I have, then you're actually going to see that when I take the correlation of this guy, what I have right here can actually be written as this. Okay, because if you take a look at this, you're actually going to write the A1, okay, because we're talking about covariation, okay. We're actually talking about covariation, okay. So I'm actually going to write A1, then I'm going to write the variance of WT minus 1. I'm going to write the variance of the, of the immediate past. Okay, so what I have here, mathematically speaking, when I decide to simplify that, there's another way to put that. But you don't need to worry about that, okay? So, and this is a 1, and this guy here is a variance of the white noise, okay? This is the variance of the white noise, and don't forget, the variance of the white noise at different period is T sigma squared W. Now, this is for the numerator, okay? Now, if I want to talk about the denominator, I'm actually going to be talking about this guy here, and I'm actually going to talk about this guy here, okay? And that's exactly what I'm trying to do right here. Now, the denominator of that, when I decided to multiply the variance of this by the variance of this, you remember the other time, what do we get when we get the variance of that? What is the variance of yt? The variance of yt is this guy, okay? And you know what? The variance of yt minus 1 will also be this guy. Take a look at what I have here. Can you see that now? So if I use this guy here, okay, to multiply itself, because the variance of yt and the variance of yt minus 1 is the same as this. When I multiply that, of course, I'm actually, going to have something raised to power 4. But when I take the square root, I'm actually going to get back to that. Now, what am I trying to say? The variance here is the same thing as the variance here. Multiplying them, finding the square root, it's actually going to give only one of them, which is this guy here. Okay? And when I have this guy here, What is the correlation? The correlation is the ratio of the covariance to that. I'm actually going to write this guy divided by this guy. So when I use this guy to divide this guy, the sigma squared W, we cancel sigma squared W. I'm actually going to have A1 divided by 1 plus A1 squared. Can you see that now? Okay. Can you see that now? So this is the autocorrelation at lag 1, for moving average of order 1. Is there anyone we want to ask question? Now, what am I trying to say right here concerning, what am I trying to say? Using the example that I used on the grocery store sales, okay, where coupons are not observed, okay, and they actually have effects on the volume of sales. Okay, now what I'm trying to say right here is just to look at it, just to investigate the correlation at lag 1. Okay, and what am I investigating? I'm trying to look at the covariation. I'm trying to look at the relationship between what a particular grocery store make at two different time period. This they are that are one lag apart. It's just for you to be looking at the relationship between the sales on Monday and the sales on Tuesday. Okay, and this is it. Can you guys hear me?
Yes.
Okay, now if I want to do at lag 2, okay, if I want to do at lag 2, even before going for lag 2, I know that if I'm working on moving average of order 1, anything greater than lag 1, the correlation will be equal to 0. Okay, and you know what, if you pretend as if you don't know, if you pretend as if you don't know, you can actually prove that that is equal to 0. Now in exam, what if you are asked, like for instance, you are giving lag 2 right here, and I give you lag 3, and I'm talking about moving average of order 1, automatically you know that your correlation will be equal to 0. But do you know an examiner can ask you to prove, can ask you to show that that is equal, that will be equal to 0? Okay. Now, if you similarly, if you want to go by the way we do before, this is YT. This is like talking about two lag apart. Okay. This is YT, and this is the YT for moving average of order 1 is this guy here. Now, what is the YT minus 2? I'm actually going to subtract 1, subtract 1, subtract 1. I'm going to have this. Then I need to figure out the numerator. So the numerator, okay, what is the covariance of YT comma YT minus 2? I'm actually going to write the whole of that and the whole of that. Can you see that now? And when I have this, I told you similarly that mu is a constant, okay? Is a constant. So this is the same thing as this, okay? And you know what? When you have this guy here, when you try to find the covariance, okay, it's actually going to give you 0. It's actually going to give you 0 because you're actually going to see yourself between WT minus 1, WT minus 3, and so on like that. And we are told that right noise at different period, there shouldn't be any connection between them. Therefore, the covariance will be equal to 0. Therefore, for autocorrelation for MA of order 1 model at lag 2 is going to be equal to 0, not only at lag 2, at a lag greater than 2, greater than 1, because we're talking about moving average of order 1. Okay, so this is from theoretical, from statistical theory. Okay, let's now look at MA of order Q population model. Okay, we want to generalize that, we want to go beyond order 1. Okay, so if I have this population model, this is a population model. There's something I want you to understand right now. There's a difference between population model and a fitted model. Okay, so this is a population model, and of course, the fitted model. Now, if you take a look at what I have right now, Okay, I got the combination of the current shock, the immediate past shock, and so on like that. So these are white noises. Okay, now that is to order Q. That was what that was the reason I'm trying to say order Q. You see that now? Now, if I now want to generalize now, if I want to look at the trend, okay, when we're dealing with order one, when we know the other one actually stopped right here, right? When we're dealing with the other one, okay, what do we have for the one? For the one, the variance was sigma squared W into 1 plus A1 squared. Do you remember we stopped right here? When you go to order two we stop right here. Order three, we stop at 3. And for order Q, you're actually going to go. You remember what I was talking about? When we're talking about the variance, I'm going to show you right now. Do you remember this one? Okay. So this one is when I have for order 1, okay, when it is extended, this guy here is actually going to extend. It's actually going to be a1 plus a1 squared plus something squared, it's going to continue that way. Okay, and that's why we're trying to generalize that right now. Okay, so can you see that now? And when you take a look at what I have right here, it means the variance of yt will actually be greater than the variance of a white noise. And the reason why it is greater is because of this guy here, because this guy is actually going to be, this guy is going to be greater than 1. Okay, why is it going to be greater than 1? This is 1 and this is squared. Okay, automatically from here to here this will be a positive, and when you add 1 to that, it will be greater than 1. It is only when all these guys are 0 that the variance of yt and the variance of white noise are actually going to be the same. So they are not going to be the same. The variance of yt should be greater than the variance of the white noise. Okay, and you know what? Autocorrelation are equal to 0 after lag Q. You know that? So if I'm talking about MA of order Q, it means if I want to talk about autocorrelation at lag Q plus 1, and that would be 0, and so on like that. Okay. Now, so, and you know what? MA models are always stationary. Okay. MA models, they are always stationary. And the reason why they are always stationary, you remember the other time that we were assuming that the variance of white noise at different period are the same. And the mean of that at different period, I'm going to show you something right now that I showed you before when I was computing the mean. Okay, when I was computing the mean, you're actually going to see that I said expected value of WT equal to 0, expected value of WT minus 1 equal to 0. So the mean and variance, do not change systematically over time. Okay, so, and that was why we said the MA models are always stationary. Okay, the reason why they are always stationary, you're actually going to see that there is no way this is going to be defined for all. If you look at what I have here, this is defined for all real numbers. It is defined for all real numbers. Any real number that you put right here, is that negative or positive, because you got a square, it's actually going to be determinate. You can determine that. Okay, and that is the reason why we said MA models are always stationary. Okay, but in a special where, if you look at what we did in ARU models, you're actually going to see that in ARU models, we have a something divide, we have a denominator, and when the denominator of a fraction is 0, okay, that fraction will be undefined, and that is the reason why stationarity, I'm mathematically speaking, okay, stationarity is required in autoregressive model, but in the case of moving average model, it is always stationary, because when you look at the mathematical architecture, it is defined for all values in real numbers. Okay, let us have a review. I've walked you through the moving average model right now, and we have also done something on autoregressive model. Let us now have a review. How do we identify an ARO of order P model? I said for the autoregressive model, when you use the ACF plot, which is the autocorrelation function plot. So, and the estimated correlation decay as lag increases. Okay, using the ACF plot. Okay, if a model is autoregressive model, okay, then what you are actually going to see in the ACF plot is that the estimated autocorrelation will decay exponentially to zero as lag increases. And you know what? Using the PACF plot, the estimated partial autocorrelation cut off after lag P. Okay, so but in the case, and if you now take a look at what I have here now, you remember we did this last time. Okay, you can see this is the ACF plot. When I say something like this, it's the autocorrelation value is actually decreasing. Okay, this is the autocorrelation plot of a time series data. This is not the autocorrelation plot of residual. Okay, now because we got two different kind of autocorrelation plots. Okay, we got the ACF for time series, we got the ACF for residual. Now when you take a look at this guy here, so when I see the ACF plot that look like this, then it means this is a autoregressive model. Okay, because it is decreasing. The autocorrelation as the lag is increasing, it is decreasing. Okay, it is going down. Okay, so that is the ACF plot, like I said. And the partial ACF, we immediately, this is autocorrelation. If you take a look at what I have here, this is the autocorrelation that has to do with the lag 1. Okay, and immediately after autocorrelation at lag 1 is actually going to cut off. Can you see that now? This, so when this one cut off, of course, I'm actually referring to autoregressive model of order 1. Okay, you remember that. And don't forget, it in the ACF, we normally start from 0, lag 0, and the lag 0 is actually going to be 1. Can you see that now? But in the partial ACF, we don't start from lag 0, we actually start from 1. Okay, so that is the partial ACF. Now, and as you can see, I said the PACF value start at lag 1 and not lag 0. Okay, but in the case of the ACF plot, it's actually going to start from lag 0. Okay, so, and if you take a look at what I have here, though I know that this is giving me an idea that my model is an autoregressive model, because this is decaying to 0. Okay, it's decaying, but I may not be able to, this may not be able to tell whether it is going to be autoregressive model of order 1 or order 2 or order 3 and so on like that. This ACF cannot tell me that. But you know what it's going to tell me? It's going to be partial ACF, because the PACF will tell me immediately after lag 1, if it's cut off, then I'm actually going to know that that is an ARO of order 1. If it's cut off immediately after lag 2, I'm actually going to know that is the autoregressive model of order 2. So basically, the ACF plot is not enough. So the ACF plot will enable you to distinguish between having an autoregressive model or the moving average model, or the combination of the two. Okay, but the PACF will actually do the job, okay, of identifying, okay, that order, okay, within the autoregressive, okay, whether it's actually going to be order 1 or it's actually going to be order 2, okay. And because the PACF actually cut off at a particular lag, at lag 1, after lag 1, it's cut off, as you can see right here. After lag 1, it's cut off. Then that is the reason why we said the AR1 model is appropriate. Okay, how do we identify the MA model? Okay, How do we identify the MA model? I'm actually going to show you how the ACF plot and the PACF plot is actually going to be. Don't forget that I told you the other time, it's actually going to be switched. Okay. Now, if you look at the PACF, okay, if you look at the PACF, okay, the plot of, looking at the PACF, the estimated partial autocorrelation decay as lag increases. Okay, the PACF. And what decay as lag decreases in AR? It is the ACF. But for the MA model, it is the PACF that decay. Okay, it is the PACF, that show decay when lag increases. Can you see that now? And why for the ACF, the job that the ACF is actually going to do right here for you to be able to know whether an appropriate model for time series data is any of other one, that is when the ACF cutoff, that is when on the ACF plot, the estimated autocorrelation cutoff at a particular lag Q. If you take a look at what I have here right now, you're actually going to see that it's actually cut off after lag 1. If you take a look at what I have in the ACF, you're going to see that the ACF actually included 0. I told you, you can see this is 1, but this is the lag 1. And after lag 1, you don't see any vertical bar anymore. So can you see that now? So please, in exam, don't actually confuse one with the other one. Okay? So when MA1 is appropriate, MA model is appropriate, and how the AR models are appropriate. Okay, so we want to have a simulation study right now. Do you remember the other time when we're dealing with the autoregressive model, we were able to simulate, okay? We're able to simulate uh, from, using the R software, we're able to simulate the autoregressive model of other 1, other 2, and so on. Do you know we can also simulate, okay, from the for MA model, okay? So you got a MA model giving us this, okay? This is the mean, okay? This is the parameter. Can you see that now? So this is a population model right now. So please know the way population model is given and know the way the fitted model is given. So we actually want to generate 2000 data set. And of course, I told you when you want to generate, you're actually going to, the white noise, will be from a normal distribution, okay? Identically and independently normal distribution, okay? Can you see that now? With mean 0 and variance 1, okay? And if you want to do that in R, okay, like I said, we set C the other time, and I'm actually going to put arima.sim. I told you before, when I say arima, whether you talk about autoregressive model, you talk about moving average model, you talk about autoregressive moving average model, you talk about autoregressive integrated moving average model, and so on like that, you're still going to use arima.sim. And you know what? I'm going to write the model list, the MA. So in my MA, I'm actually going to put my parameter. Do you know that I can declare something missing like this in exam? And I ask you to figure that out. Do you know I can ask you that? So now I'm going to show you what is missing right now. Now, if you take a look at this, you're going to put the 0.8 right here. Okay. I'm going to put the 0.8 right here. Can you see that now? And you know what? If you take a look at the ST equal to 1 is the square root of this guy here. Okay. And plus, now what you're going to put here is actually going to be 6. That is the mean. Okay. You're actually going to put the mean. Okay. Is there anyone who doesn't understand this code? Is there anyone? The other time, the difference between this code and what we did under the autoregressive, the difference lies here. Okay, in the autoregressive we wrote AR. You remember that time? But now we're writing MA. Okay. Now from the data set, and that was why I said, according to the population, the model, according to the population model, the theoretical mean is 6. Okay, this is the theoretical mean. Okay, this is the one I said you're going to put here. Now, if the theoretical mean is 6, okay, if I copy this into R, okay, and I want to find the mean, so this is going to be the mean. This is the mean that we observe. This is the theoretical mean. We may want to see whether there's a connection, whether there's an agreement, whether there's a closeness, okay, between that, okay. And when you look at the variance, okay, theoretically, if you want to find the variance here, okay, we got that variance to be 1.64. You remember, I'm going to walk you through, we did that the other time. We derived the variance for that model. I think we're still using the same model. I'm actually going to show you now. Oh, okay. I think it's not this one. So when you make use of the formula right here, okay, when you make use of the formula right here, because you know the variance of the white noise, and you know the variance, you know the parameter in your model, okay, you can actually do that to find the theoretical variance that I talk about, okay. So how do I get that 1.64? Okay, getting 1.64, of course, I use the variance of this, which is 1, multiplied by 1 plus the 1 plus the parameter, the parameter, the estimate of the parameter. Okay, so in 0.8, when you square that, that would be 0.64. And when you add 1 to that, that will give you 1.64. Okay, I'm actually making this is a theoretical variance, and the variance right here is the variance from the data set. Okay, so I'm going to call this a sample variance of the data, and this is a theoretical variance. Okay, and the theoretical variance is more or less like a population variance, because what I have here is for the population. Okay, before we collect data at all, this is what we have. And after collecting data, after simulating the data, okay, so is there an agreement between the sample mean and the theoretical mean, and the sample variance and the theoretical variance? Okay, and based of that, you actually, we can make use of the ACF plot and the PACF plot to do that. Okay, so this is from, of course, I show you the code the other time to get the ACF plot and to get the PACF plot, and this is exactly what we have. Okay, so, and you know what, we actually use what is it called, we're still talking about this model. Okay, I walk you through that the other time. Okay, so that is the model. And you know what, if you take a look at what I have right here, if you look at the ACF plot, okay, and you're actually going to see that the ACF plot cut off after like 1. If you take a look at what I have right here, you're actually going to see that this is for the what, this is for the at like 0, and this is for like 1, and after like 1. So if you take a look at that, then you can follow up with what I've been explaining. Okay, and look at the PACF plot. Okay, now if I now want to write the model now, and if I want to do how do I fit the model? Okay, for instance, if I have a data set, now this is what I want to do. You remember the other time that after simulating, can we have a way to estimate our parameters again, so that will enable us to compare the population parameter with the estimate, with the one we got from the data set? Okay, and that's exactly what we want to do right now. And if we want to do that, because I'm talking about ARIMA, AR, since I'm talking about, the focus is on the moving average. I told you the other time, there are 3 things right here. We got the autoregressive, we get the integrated, and we get the moving average. But the focus is on the moving average model. Then it means the autoregressive will be 0, the integrated will be 0, and the moving average, because I'm talking about order 1, so this is going to be 0, 0, 1. Okay, so and this is my data set. Okay, and when I run that in now, look at what I'm actually going to get. Now let us now take a look at this. You know, the regression parameter now, the parameter in the model is estimated to be 0.7996, but theoretical one was a 0.80. Can you see that now? And this is the intercept. And don't forget, intercept is the mean. Okay, what was the theoretical mean that we had the other time? The theoretical mean was 6. Okay, and look at what we actually got right now. Can you see what we got right now? Then it means this guy here is the same as the sample mean. Okay, if you go back, you're actually going to see that right now. Can you see that now? That is the mean. That is the sample mean of the data. Okay, okay. So like I said, you got the AIC, you got the log likelihood in case you actually want to compare. Like at times you could have different models on that moving average. Okay, if I change this to 2, if I change this to 2, that will become the moving average of order 2. If I change it to 3, that will be moving average of order 3. Okay, so like I said, we got a fitted model right now. Okay, now how do we make prediction, using the moving average model? Can you guys hear me?
Yes.
Okay, now if there's anyone who want to ask question, please make sure you ask. Okay, now based on the model, how can I really predict ahead? Okay, I want to specify. This is a code in R. So putting 3 here means I want to predict the next 3 observation. Okay, don't forget that we use 2000 data set, right? We use 2000. Let me take you back. We use 2000 data set. Look at that, n equal to 2000. Okay, then how do we predict the value for 2001, 2002, and 2003? So that would be the next 3 observation. Okay, how do we do that in R? Okay, I'm actually going to write this one, and these are the values that actually come out. So these are the values. This is for 2001, this is for 2002, for 2003. Okay, so I think you can actually see that now. So what we're trying to say, so this is what the arrow is actually going to give you. Can you see that now? But if you want to do that manually, okay, if you want to use a formula to do that, if I want to use this to make prediction right now, okay, how do I go about that? Okay, now if you take a look at what I have here, okay, if the volume of sales in my company, okay, if I want to predict the volume of sales for 2001, for 2002, and 2003, so what am I actually talking about? Okay, if I want to predict the volume of sales, okay, for 2001, okay, now when I say 2001 right here, I'm not actually talking about, I may be talking about year, I may be talking about daily, I may be talking about weekly. Okay, so let me assume that the data point, the last data point, which is 2000, let me assume that actually fall on Monday. Okay, I'm going to be assuming a daily sales right now. Okay, now if the last sale is for Monday, okay, and I actually want to predict what is going to be the sales for Tuesday. So this is Tuesday right here. Now, what I'm trying to say in essence is that I can only make that prediction for Tuesday using the surprise for Monday. This is a surprise for Monday. This is a shock for Monday. This is a white noise for Monday. This is not a white noise for Tuesday. Okay, this is a white noise for Monday. Okay, So I'm actually going to take that into consideration. And how do I figure out the white noise for that day in R? I'm actually going to write mode $sign residual, and I'm actually going to put 2000, okay? And that is actually going to give me this. Then I'm actually going to plug in that here, multiply by this, add it to that. It's actually going to give me the value for 2001. So what I'm doing right now, I'm actually using the model. I'm doing that manually, okay? I'm doing that to predict. But if you want Arrow to do that for you, automatically, Arrow is just going to give you the result, okay? Okay? So now, if I want to predict for 2002, maybe 2002 is what happened on Tuesday. Oh, sorry, this is for for Tuesday. I'm predicting for Tuesday. Okay. So when I'm predicting for Tuesday, this is a surprise for Monday. Okay. But right here, I'm actually want to be predicting for Wednesday. If I want to predict for Wednesday, I'm actually going to use a surprise for Tuesday. Okay. What do I mean by surprise for Tuesday? Is shock on Tuesday, is white noise for Tuesday. Okay. And you can also write the code in R. Okay, you're just going to put 2001 right here. It's going to give you that plugin. You get your result. And if this is for Wednesday, then you can do the same for every other one. And or do you understand that one now? You know what to put here, okay? And identify the appropriate time series model based on the ACF plot and the PACF plot. Now you know how to do that, okay? You know how to do that, okay? And you know what? Based on what I have right here, if you take a look at this, okay? If you take a look at this, look at the ACF, look at the PACF, look at the way the PACF behave, and look at the way the ACF actually behave, okay? So, and when we're generating the model, I actually want to take you back now. When we were generating the model, we actually generated the model based on moving average of order one. Can you see that now? Based on the moving average of order one, okay? So we generated the model, okay? Now, if you now come here right now, if you take a look at what I have right here, looking at the ACF, okay, and you're actually going to see, if you look at the ACF here, look at the bar here, look at the bar here. This bar is actually corresponding to uh lag 1, and this is corresponding to lag 2. And you're going to see that after lag 2, what happened? It cut off. When ACF cut off, then that should be MA, and that will be MA of order 2. Look at that. You know, when ACF cut off, then you are referring to the MA models, okay? And uh, the PACF will be the one that will now be decaying. I think you remember that. And that was the reason why, if you take a look at what I have here, it's the appropriate model is MA of order 2. Do you know that examiner can give you something like this? Probably in the multiple choice. An examiner may ask you to identify which model is the MA of order 1. If you only look at this guy alone, that's why you need to look at both the positive side and the negative side. Okay, some of you may go and choose MA for that one. No, it is not. Look at this guy. This is at lag 1. This is at lag 2. Is there anyone who want to ask question now? Is there anyone? And let me tell you this before you ask your question. What I have right here is the ACF and the PACF for this model. Okay, and if you take a look at the model right here, this is a moving average model of order 2. Okay, this is the moving average model of order 2. Okay, and do you know that from a graph, from a plot, I can write out this? Do you know that? Okay, do you know I can write out, I can have the knowledge of this from this graph? Now, how do I know? Take a look at this. It's 0.8. Okay, this guy here. Minus is 0.2 is this guy here. Take a look at that. Okay, I can basically write out that. Though from this, I may not be able to know the the mean. Okay, I may not be able to know it. But what I'm trying to tell you, you'll be able to know this and this guy here. Is there anyone who want to ask question? Is there anyone? Can you guys hear me?
Yes.
Okay, let me just check it. I want to see if everyone are listening right now. Okay, okay. And the code, if you take a look at what I have right here, if you want to simulate for MA or for that too, okay, you actually gonna I can ask you to tell me what is missing right here, okay? So right here, of course, it's gonna be 0.8 and minus is 0.2, and you know that right here you're actually gonna have 12. Okay, now, and if based on this model, if you want to have the times series graph, you're actually going to use this code. If you want to have the ACF plot, you're going to use this. You want to have a PACF plot, of course, you know that. Okay, is there anyone? This is going to be the end of the first material. Okay, is there anyone who want to ask question? Is there before I go into the last material? Is there anyone? Somebody said, maybe I missed this, but for the fitted model in slide 13 and 14, what happened to WT? Is it not there? Is it not there because expected value of WT equal to 0? Let me see what you're talking about. The person said, what happened to WT in slide 13? Let me see slide 13. Let me see what is talking about. Give me 1 second. Okay, this is 13. This is okay. Uh, if you take a look at what I have right here, okay, you have asked a very good question that what happened to slide, what happened to WT? Underestimation, okay, if you have a car, okay, then we are assuming that value to be equal to 0 because the expected value of WT equal to 0. Does that make sense to you right now, the person that asked that question? Okay, let me see. Let me read the chat. The person said yes. Okay, that is going to be the end of that lecture. I hope you guys really enjoy the lecture. I'm actually going to go into the next one right now. So give me 1 second because, like I said, I got two materials for you today. Okay, and today being the last day. Okay, the last lecture day because tomorrow I'm actually gonna start review, okay, before I give you enough time to prepare for your exam. Okay, so I'm trying to open the next material right now. So give me 1 second while I'm trying to do that, okay? Are you guys hearing me?
Yes.
Thank you so much because I really want to know if you guys are hearing me. I want to apologize that you are not seeing me right now because I'm trying to manage that. Okay, so I need you to confirm if you are seeing this right now. This is going to be the last lecture. Can you guys confirm if you are seeing time series analysis part 7 case study?
Yes.
Okay, uh this is going to be the part 7, which is going to be the last in the series, or of the time series analysis that we have been doing. I call this a case study, okay? Based on what we have learned, okay? Based on what we have learned, we actually want to apply that, okay? And we're also going to revisit what we've done before in time series. So we're going to make it uh, as you know it's going to be more of application, okay? So give me 1 second. I'm actually gonna okay. Now we want to have a study of Arctic sea ice extent, okay? Like we want to put, just like what I said, we have walked you through different kind of models in time series. And what I actually want to do right now, I want us to have a case study, okay? Just like you got a project that you want to work on and stuff like that. Okay, but the focus is actually going to be on study the Arctic Sea ice extent, okay? Now, when you take a look at what I have right here, so looking at it, looking like the map of the world, okay? You can see the Canada, you can see Alaska, Russia, and so on like that, Europe, and so on like that, okay? Now, we're talking about the study of the Arctic Sea ice extent, okay? If you want to have the access to that, you can actually, navigate this particular link, okay? And, you know, these are the people that actually work on this, okay? So you can actually go through that. Okay, so sea ice extent is the area, okay, of sea that has more than 50% ice. So any area that have more than 15% ice, okay, is called the sea ice extent, okay? So the satellite images, help scientists record the sea ice extent, okay? So they can use the satellite images to be able to they want to have the record of that, okay? So to tell you that scientists are really doing a very great job. And there are things that change over time, okay? It has a time series component in it because these ice, these actually change. The sea ice extent actually change over time, okay? So, and you know what, like I said, the sea ice extent fluctuates seasonally. Of course, you know that in the state of Minnesota, in the state of Illinois, uh, Massachusetts, and so on like that, of course, some states in the United States, you know, there are some seasons that we have a lot of snows, a lot of highs, and we got some season that we do not have, okay? Like right now, we don't have something like that right now because we are more or less in the summer, okay? And so the ice, the sea ice extent fluctuate seasonally, like I said, and reaching the largest amount in February or March and shrinking to the least amount in September, okay? So which means it is seasonal and it is, it changes, depending on time. We're actually going to use the September ice extent data, okay, 1979 to 2018 for analysis. Okay, this is the data set that we have right here. Okay, this is a data set. Like I said, we actually go from 1979 to 2018. Okay, so to 1979 all the way to 2018. Okay, and this is the variables in the data set. If you want to load the data set in R, okay, this is actually the way to load that, okay? And of course, when I write I is equal to that dollar extend, data extend, I'm actually going to have the access to that, okay? Excuse me. And if I want to plot the series of data, okay, over time, okay, this is what I'm actually going to use, okay? So that is for the time plot. So now, like I said, when you do that, this is it. What I have right now is a time plot. And you can see it over time, okay? You can see that now. So this is the expression. If you want to measure the directional movement, okay? And of course, you know where we normally have that, right? You know why they say Alaska, United States, Canada, Russia, and so on like that, and some part of Europe. Can you see that now? You see what I'm actually talking about? Okay, now the question now is if I have, let me tell you this. When you have your data set and you're working on time series, the very first thing you need to do, you need to exploit your data set, okay, by trying to us, you need to plot, you need to have you need to have a time series graph, okay? When you have a time series graph like this, like I said, this is where you're actually going to start from, okay? And here the question now is, can I fit a time series model to this data? And that is a question you're actually going to ask ourselves, okay, with the way it is right now. Okay, now, but if you really want to do that, then you need to first check stationarity, okay? You need to check for stationarity, okay? But I told you the other time, for autoregressive model, the stationarity is actually required. The condition of stationarity is required. For the moving average model, though the condition of stationarity is not that required, but uh, the condition of invertibility, I'm actually going to tell you that, okay? So that is what I'm actually going to first talk about. Now, and that was why I said when building a model, we would like the nature of the relationship to stay stable over time. That is an assumption, okay? Even though it may not that stable over time, but we're talking about on average, okay? And that was the reason why we said there shouldn't be a systematic change in the mean over time. And there shouldn't be a systematic change in the variance over time, okay? And in that world, we are actually what we're talking about, it has to be stationary. Otherwise, we couldn't use a model built from early values to forecast the relationship later. So which means if this condition is not actually satisfied, it should be impossible. Even if we do that, even if we find a way to do that, we cannot rely on that model. Okay, you remember the other time that if the condition of stationarity is not met, I walk you through differencing. Okay, we do differencing the other time. Okay, so we can difference, okay, to be able to know, because you know why? Because when you take a look at the data set that I have right here, you can actually see that there is possibility that the mean of this is changing over time. Okay, and that is the reason why when the mean is changing over time, there's possibility that the stationarity assumption has actually been violated. And how do I go out of that situation is to difference. Okay, what I'm actually showing you right now is a code to difference. Okay, then I need to replot, I need to have the plot of the difference data again. Okay, and I'm differentiating at like 1. Okay, I need to have that again, and I'm going to take a look at that to see whether the mean is now stable over time. And it is not all the time that when you difference at like 1, that is actually going to work. You still need to revisit your intervention and see whether you need to difference again. Okay, so, and that was why I said taking the difference at like 1 actually help us to remove obvious violation of stationarity. We've done that before, right? Okay, so that is the essence of differencing. Okay, if a time series data actually have a problem that has to do, there's a violation of stationarity, then there is no problem. What we actually going to do, then we're going to difference. When we difference, of course, when we take a differencing, then everything is going to be fine. Okay, and of course, how do I know if everything is fine? Of course, I told you the other time, I actually need to have the plot of the ACF, and not only that, I'm actually going to have the plot of the PAC here. And if you take a look at what I have right here, okay, when you take a look at what I have right here, you can really tell whether the appropriate model is actually going to be the moving average model or the autoregressive model. Okay, so now after observing the ACF plot and the PACF plot, I choose three candidate model. Okay, I choose because at times the ACF plot and the PACF plot may not give the exact picture of what we're looking for. Okay, I'm actually going to tell you now, why do I have to think about the autoregressive model of order one? Okay, why do I have to think that, okay, one of these suspect model is autoregressive model of order one? If you take a look at this guy here, after lag one, okay, after lag one, the lag one here is the estimate of that parameter is negative. So after lag one, it's actually cut off. Can you see that now? That is why we're thinking in that sorry, uh after lag one it's cut off. That is where we're thinking in the respect of MA of order one. Okay, I wanted to say MA of order one. Okay, so I wanted to say MA of order one. Give me 1 second. Okay, now you remember for MA of order one, it is the ACF that cut off, right? Okay, now if that really happened, then if you take a look at the partial ACF right here, okay, if you look at the partial ACF, for the case of, moving average, for the case of autoregressive model, okay, we expect the partial ACF, we expect that, okay, something should cut off at a particular lag, right? We expect that, right? But basically looking at what I have right here, you're actually going to see that this is very more or less very close to the line, right? And one may be suspecting that if I have just one, if you consider just this lag right here, you may be thinking that is an autoregressive model of order one. But if you consider the three right here, because this one and this one, they are actually very close. Okay, they are actually very close. If you take a look at what I have now, let me say that again. If you take a look at this, under the partial ACF, this is for lag 1, this is for lag 2, and this is for lag 3. Okay? Now, when you take a look at this guy and this guy, okay, you're going to see that you may likely going to say that it's cut off after lag 3. Okay? And somebody else can also argue that it's cut off after lag 1. But somebody may say it's cut off after, this is for lag 1. Somebody may say, oh, it cut off after lag 1, which is why I'm saying it's AR1. Another person can say, no, look at what about this guy here? It's actually cut off after lag 3. And that is the reason why I have AR3. Okay? And if you look at the ACF, okay, when you look at the ACF, when the ACF cut off after, this is lag 1. When it cut off after lag 1, that is MA1. Now, is there anyone? Can you now see the reason why using these two charts, two plots right here, is suggesting three of this, any of this? Is there anyone who have a trouble time understanding how the two plots right here are actually suggesting the MA1, the AR1, the AR3? Is there anyone? Can you guys hear me?
Yes.
Yes.
Okay. Does that mean you guys understand what I'm trying to say right now? Does that mean you guys understand? I need you guys to say yes if you understand before I move. Oh,
Yes.
thank you so much. I need another person. If you cannot say yes, you can actually shout and say yes, any of that. So I've taken number one person. I'm actually waiting before I go to the next slide because this looks so tricky, okay? And I need to know whether you guys understand why this particular two plots right here are actually suggesting MA1, AR1, and AR3. Now, I need someone to, if you don't understand, you just need to indicate no, or you say no. But if you understand, you just say yes, or you indicate yes. Is there anyone? Okay, I'm going to check my chart right now. Okay, I got yes, yes, yes. Okay, good job. Okay, thank you for that. Before I move again, okay, let me read another chart coming. Okay, somebody say yes again. Good job. Now you know the reason why it is MA1. Why it's suggesting MA1? Because in MA1 it is the AC when ACF cut off at lag 1. This is at lag 0. This is lag 1. After lag 1, there is no anyone again that come outside the blue dotted line. So that is actually suggesting MA1. But if you take a look at this guy here, okay, when you take a look at the PACF, when you want to talk about cutoff, if this is after lag 1, you can say it's cutoff. That's the suggest ARM. But if you take a look, this one came out again. This is for lag 1, lag 2, lag 3. And after lag 3, it's cut off again. And that is the reason why we got three potential model. We got three candidate model. Now, the question now is, in a situation where we actually have a kind of conflicting of interest, okay? If you take a look at the ACF and what the ACF and the PACF are suggesting right now, they are actually suggesting three models, and this will now become our candidate models. They're going to become our candidate models, okay? So we choose three models, so they're going to become our candidate models. And you know what? We got a way to investigate which of the model is the best, which of the candidate models suggested by the two plots. We got a way to actually investigate that. Okay, let's start with the first one. You know, the first one is MA1, right? We're going to start with the first one. Starting with the first one, don't forget that we've differenced our data, right? We're still using the data on the eyes, okay? We're still using the data on the eyes. We difference that, okay? Now, we want to estimate the MA of other one, okay? We have estimated that this is the result. Can you see? Because this is going to be 1, or that is going to be 0, 0. So that is a MA of order 1. And you know what? When we have more than one model, and that is the reason why we're going to be comparing them using the estimated sigma, or using the log likelihood, or using the AIC. Okay. Now, for the AR1, this is a model. Of course, you know AR1 is going to be AR of order 1 integrated of order 0, MA of order 0. That's why you have this, okay? Now, this is the result. Can you see that now? Okay. The next thing is AR of order 3. Can you see that now? In the AR of order 3, it's going to be 300. And this is going to be, of course, you're going to have a lot of predictor AR1, AR2, AR3, because you're talking about AR of order 3. Okay. Now, we have been able to estimate parameters in the candidate models suggested by the AC plot and the PACF plot. Okay, you know, the ACF plot and the PACF plot actually suggested three candidate model that we are actually estimating, you know, right now. Okay, we are fitting these models to, I mean, we're fitting the three candidate model to the data set right now, and we actually want to have a way to compare them. Okay, before we compare them, can we look at the ACF of residua? Like I said, for those of you who, if you want to work on a time series data, and in a situation where you got different kind of model, competing models, you actually need to investigate them the way I'm doing right now. Now, I started with the MA of order 1. I've estimated the MA of order 1. This is what I have. I've estimated the ARO of order 1. This is what I have. I've estimated the ARO of order 3. This is what I have. The next thing that I'm actually going to do right now is to be able to investigate the each of this model, for diagnostics. Okay? We need to evaluate the models. And if we want to evaluate model for diagnostic, we're actually going to talk about the ACF of residuals. I'm going to say that again. I've walked you through this before. Okay. Now I want to investigate the MA for that one model. Okay. Now in the investigation, what do I have? Okay, what is the theoretical assumption of a time series model? The assumption is that the residual in the model should behave like a white noise. Okay. Now, how do I know the autocorrelation function of the residual behave like a white noise? Okay, now it's going to behave like a white noise, of course. If I plot the autocorrelation, estimated autocorrelation at different lag, I expect, this is the autocorrelation of the autocorrelation of the residuals, okay, at different lag, okay, all of that must within, okay, the blue dotted line. The only one that should be outside the dotted line should be the one that corresponds to the autocorrelate, to the one of lag 1. Okay, that is the only one. Okay, so what I have right now is the autocorrelation of the residual. Though somebody may want to argue that with me right here, there is one that is outside here. But don't forget that I also told you the other time, it is not necessary that all of them should be out, because we're actually going to have 5% level of significance, okay? Now, this is for the first model, okay? Now, we're going to go for this second model, the second candidate model. We actually want to look at the autocorrelation function of the residual for the AR1. If you take a look at what I have right here, you're actually going to see that one is out here. This is more or less out. Can you see that now? It is only one that is out right here. Okay, at probably like 11. Okay, take a look at that. But if you take a look at right here, you're actually going to see that probably in between, maybe like 2, something like that, you're going to see something out, right? And if you look at here again, you have another one out. Okay, for the autoregressive model of order 3, you're actually going to see that, in fact, all of them are within. Can you see that now? All of them are within. Can you see that now? If you take a look at the 3 models, the 3 models are actually good. But you know what? There's always going to be the best among good models. I think you know that. Okay. Now the question here, do the residual behave like a white noise? Okay. Do the residual behave like a white noise in the first model in the MA order 1, in the autoregressive of order 3, in the autoregressive of order 1? If you take a look, I told you before that all these models are valid. They are valid because a good number of that is actually within, they are bounded within the blue dotted line. If you take a look at that, okay, all these models are valid. So, which means the ACF and the PACF, they've done a very great job in trying to suggest to us, these 3 candidate models, okay? The 3 candidate models are actually valid. And they are valid because I'm actually investigated the autocorrelation function of their residual, and I realized the majority of the autocorrelation actually are within the blue dotted line. Okay, if the models are good, if they are equally good, and like I said, we're actually going to identify the best of them. Okay, and how are we going to identify that? Then we're actually going to look at the variance of each model. We're going to look at the variance of each model, and we're actually going to look at the AIC. Of course, you have heard about AIC before. We have used this AIC to decide in the, for model selection in linear regression. I think you know that. We're also going to use AIC right here. When you take a look at, I quickly want to take you back into the output. Now, when you take a look at the output, you actually going to be sigma square estimated, right? You're actually going to see the AIC, okay? Every of the model has that, okay? Since these three models are equally good, then we can now compare. But let me tell you something. If a model does not pass a test of diagnostic, then that model shouldn't be considered at all. Okay, before I'm actually going to go into comparing the variances or comparing the AIC and stuff like that, that particular model must first pass a diagnostic testing. Okay, so because they are equally good, and that is the reason why we now want to compare them now, just for us to be able to figure out the best. Okay, now these are the variances. Well, of course, we actually got all this. I extracted that from the arrow output. Okay, so this is just trying to tell us the number of parameters, okay, in each of this model, okay. Of course, the MA of other one, the ARO of other one, we actually going to have two coefficients, okay. And somebody is actually going to ask me, what are the coefficients are we talking about? Of course, you're going to have, if I take you back, you're actually going to see for yourself right now, for MA1, you're actually going to see this one and this one, okay? For AR1, it's actually going to be for this and this. I'm talking about the intercept and, the regression parameter. Okay, so, well, for the case of AR of order 3, of course, you're actually going to have 4, okay? It's more or less we're talking about regressors, okay? Regressors, more or less the same thing as the number of parameters, okay? And that's exactly. Now, if you want to look at the minimum AIC, because the models with the minimum AIC is actually going to be the best model. And you know what, the one with the minimum AIC is 68.29. Well, the one is 68.29, and that actually corresponds to the MA of other one. Therefore, well, using the AIC, it is the most preferred. Okay, the MA of other one is actually the best model among the three competing models. Somebody is actually going to say, but well, look at the variance. If you are looking at the variance, ARO for that 3 is better. But you know what? AIC is superior to the estimated sigma squared. Okay? And that was why I said, no, AIC is one of the ways to measure the model performance. Okay? You can choose other measurement as well. Okay? But you know what? Most of the statisticians actually believe that the AIC, in one way or the other, kind of superior when you are talking about model performance. Okay, I'm going to tell you there's a difference between model performance and prediction performance. Okay, predicting ability of a model. Okay, I'm still going to you're still going to know about that, but what I'm talking about right now, I'm actually talking about model performance. Now, since the AMA of other one is good, and there's another thing I want to show you. If you take a look at the MA of other one right here, you're actually going to see this is the only one. that actually come out. But when you take a look at ARO for that one, you have like two. Okay, when you look at the ARO of order three, we also have one, but only that the MA, you know, if I want to rate this one now, of course, it's trying to say that these two are, are far better than that one. Okay, now the next thing I actually want to talk about right now that the MA for that one is appropriate, and that's exactly what I'm actually going to use. That's what I'm going to use for my prediction, okay? That's what I'm going to use for my prediction, okay? Now, if you look at the data set that we're talking about, the Arctic ice extent, you're actually going to see that the data actually stopped in 2018. I'm going to show you right now. I think it's a yearly data. Okay. It's a yearly data. It's going from 1979. Okay. To 2000. I'm going to show you right now. To 2018. Okay. So which means a yearly data. Okay. Then it means I can actually predict for 2019. Okay. We can actually predict. And you know what? If I want to predict, I actually going to use the best model. Okay, to make the prediction, okay, the MA for the one after performing the diagnostic testing, okay, and using the AIC, being because it has the smallest AIC, is the best model and is the one that we are actually going to use in making our prediction, okay. So we want to have a prediction for 2019. Of course, the last data point actually stopped in 40, okay? It's 2018, the last data point stopped in 40. I'm actually going to predict for the data point in 2019, okay? And this is going to be the code, okay? I'm actually going to base that on the MA of other one, okay? Can you see that now? That is going to be my prediction right here. And what I have right here now is actually going to be the standard error, okay? Because the prediction will actually come with a standard error, because we also need to have a way to investigate, okay, the prediction, okay. So, and that is the reason why the standard error will actually tell us how reliable is a prediction, okay. Because if I have a lot of prediction, okay, if I predict for so many values ahead, you know that I can also do what I call prediction error, okay. I can talk about prediction error. I can measure prediction error, okay. So now what I'm trying to talk about, if you take a look at what I have right now, you're actually going to see, why do we have this here? Don't forget that we were no longer using the original data set, okay. The original data set was stationary and we needed to difference. I think you remember that. We needed to difference. And when we difference, okay, so what I have right here is actually going to be data Y40. Okay, it's actually going to be data Y40. And don't forget the data Y40 equal to Y41 minus Y40. Okay, I think you remember that. That is a relationship they actually have. So what I'm actually going to do is that if I want to know the last observation, which is Y40, the Y40, I'm just going to do ice 40. No, my data set is ice, you know that? And the last data point, the 2018, is 40, you know that? So 4.71, we actually is the data set. Do you know that now? So if I have that one now, so my Y40 equal to 4.71. Okay, so if my Y40 equal to 4.71, if I want to know the prediction for Y41, okay, don't forget, I actually want to predict for Y41. What I have here is not the prediction for Y41. Don't forget that we have difference our data set, okay? We have difference our data set. This is what is actually going to come from there. So based on what you have right here, you will be the one that will actually determine the Y car for the predicted for 41. Okay, this is in 2019 right now. Okay, can you see that now? So, and this is a relationship they have. So the only thing I just need right now is just that I'm actually going to add the last data point in 2018 to this guy here. That's exactly what I'm doing. And this is going to give us 4.45. Now, this is our prediction for, for the first data point in 2019. Okay, if you want to use the ARO for that three, because we know that the three models are fine, okay, but only that one is the best, okay. But if you also want to use this one now, if you want to use the ARO for that three, this is the model. You know how to write the model. You know how to write that. You know that we're going to write because we have difference. We actually need to put all this one until you know that because we difference. Okay. And don't forget the 0.07 that you have right there. I'm actually going to show you in the ARO of order 3 right now. The 0.07, can you see that now, is the intercept and is the mean. Do you remember that? Is the mean. And that's why we're subtracting that. I'm actually going to show you now. So that is why that's why you added it here. Can you see that now? Can you see that now? So can you see that now? And you know what? The parameters, okay, this 0.7 minus 0.75, minus 0.52, minus 0.36. This is a way you're actually going to write a fitted model for other regressive model of order 3 in a situation where you difference your data set. When you don't difference your data set, it's not going to look like this. Okay. And if you want to use a arrow of order 3, the very first thing you actually need to do is first, though you actually want to predict for 41, okay, but you need to first predict the data of Y40, okay. You know, you know the actual value for Y40, but what about the change? You don't know that, okay. You don't know that for Y40, okay. So you need to first predict that, okay. Now, if you want to predict that one now, so if this is 40, okay, if this is my last data point, if I put 40 right here, look at that. I'm putting 40 right now, okay? When I put 40 right here, and I'm going to put 40 in all of them. So 40 minus 1, 39, 40 minus 2, 38, 40 minus 3, 37. Can you see now? I'm trying to plug in 40, okay? When I plug in 40, what do I want to get? I actually want to predict, you know, the data, okay? Data of, data cap Y40, okay? That's actually what I want to predict. But you know what? If I want to if I want to predict for data of Y40, then I need to use the actual difference, okay, of Y39, Y38, and Y37, okay? That's exactly what I'm going to do. And you know what? If you want to, in R, you just need to write difference, 37 to 39. Look at that. For 37, for 38, for 39, in R, it's going to give you, if you write that one or if you write this one, it's actually going to give you. So which means you know the value that you're actually going to plug in here. You know the value you're going to plug in here. You know the value you're going to plug in here, okay? So you got for 37, for 38, for 39. So what you have here is the difference. Look at that. That is a code difference. Okay, can you see that now? When I plug in that one, then I'm actually going to get this, okay? So plug in that one now with automatic. So you can see that now. So I'm trying to tell you what each of that represent. Can you see that now? So by the time you now plug in that, when you plug in this value right here into here and you solve the equation, you'll actually be able to get this, okay? You'll be able to get this, okay? Now when you get this one now, then the next thing that you're actually going to do, okay, you need the eyes for 40 because what you actually want to get is white card 41. Don't forget, if you want to get a white card 41, you need a delta cap Y40 and you need the actual 40, okay? Then the next thing that you're actually going to do, if you get that one now, then you need to add that together and this is going to be the actual prediction, okay? So this is going to be for for the first point in 2019. And what did uh AMA for that one predicted? AMA for that one actually predicted 4.45, but AR of order 3 actually predicted 4.49. Can you see that now? It actually predicted. Is there anyone who have a trouble time understanding what I just explained right now? Is there anyone? Is there anyone? Okay. So silence implies that you guys are good. That is going to be the end of my lecture for today, and the end of the lecture in this semester. Like I said, I want to appreciate everyone for attending my lecture today. I hope you guys enjoy my lecture. Make sure you stay safe and do have a good day. But before I go, I want to tell you that tomorrow I'm actually gonna walk you through practice question. Today, I'm actually gonna upload the practice questions. Okay, for the final. Today, I'm actually gonna do that. Okay, so make sure you watch out. And for all outstanding assignments, okay, all outstanding assignment will be graded. Okay. Now, let me tell you this. I want to give this opportunity for those of you who have missed assignments in the course of the semester, because I know we are not in a perfect condition right now, because I know we're in the middle of pandemic. Okay. So because of that, I'm going to give an opportunity to, to give you another, or to give those kind of people another opportunity to be able to complete their assignment. So if you fall into that category of people who one way or the other miss assignment, okay, you can actually send to me, though, uh, you're actually going to get some points. Like, I can assure you 90%, because in order to justify, in order to be fair to those who completed assignment on time, okay, yeah, so you, it's going to be marked, you know, 10% will be out of that, okay, will be deducted, okay. So, but you can still have 90% back, okay. It's like you're not going to lose if you don't do, for those of you who miss assignment, if you don't have opportunity, it's like you've missed that, okay. It means you have a zero for that, but I'm giving you opportunity to have a 90%, for you to be able to, not to lose all the mark for partial credit, okay? And I'm guaranteeing 90%. And the reason why I'm taking it to be 90% is because we're in the middle of pandemic, okay? But you got to make sure you complete that. If for those of you who will request, when you request and I send the makeup assignment to you, I'm going to put a date, okay? And you have to make sure no extension this time around for that. No extension, because the university is expecting, the registrar is expecting results, okay, 2 days after the final, 2 days after the final, okay. And that's the reason why whatever you want to do, you got to do that this week, okay. So I want to thank everyone once again for attending my lectures. And I also want to appreciate you guys, for listening to me, okay. I'm not the one that doing the great job. You guys are the one that doing the great job, because you guys listen to me. Because even if if somebody happens to be the best professor in the universe, in the world, if a student did not actually listen, of course, there is nothing to learn. But you guys actually listen. You guys complete your assignment. You guys ask some questions. You guys have been wonderful, okay. In fact, I'm highly you know impressed by the way, by the attitude you put into this class. So I want to appreciate, I really appreciate, you know your cooperation, okay. And let me tell you this. uh a philosopher said, and I quote, "The road to success is narrow, and everyone would like to pass through the narrow way. But going by the accommodating capacity of the road cannot contain everyone at a time. But why? Because it says some people will go. Why some people will wait? Who are those that will go? Who are those that will wait? And that very question is left to every individual in the world to answer. But you know what? Make sure you continue to be in the race of success until you are classified among the greatest in the world. Okay? Continue to be in the race of success. Believe in yourself. Believe you can get something done. Okay? Even if you have challenges, you only need time to figure that out. Don't have a difficult mindset. Okay? Be optimistic. Okay? Be optimistic. Believe you can get it done. Believe you are actually going to be the best. Believe that whatever you lay your hands upon, believe that whatever you do, you're actually going to be successful. Always make a try, okay? Always believe in yourself. Believe in what you can do. Even if you have not had A plus before, believe that this time around, I'm actually going to get an A plus, you know. So if you have that belief in yourself, if you have a very strong determination and you put all necessary machinery in place, I actually want to tell you're actually going to succeed. I'm actually believing that. You're actually going to succeed. I, you know, uh, my hope for my wish for you is that every goal in your life that you guys have set, you know, you're actually going to achieve that. That is it. You're going to surpass all expectations. Okay, you're going to do well, and by the time you join the larger society, okay, you're actually going to contribute, and society will feel your impact positively. You're going to affect the world positively. So I want to thank you once again. So until tomorrow that we see again, make sure you stay safe and do have a good day.